Thank you, Peter, for the introduction. I feel like you could even present the paper yourself. Yeah, so my name is George Merino, and Nicola and Chang are here with me. We can have the other participants on the paper, but yeah, again, we'll be going into details on how to integrate data in digital twins for the built environment, especially in the operations and management phase. So yeah, this work is actually part of a bigger initiative in the UK, where we are trying to digitalize our infrastructure and towards a national digital twin level. And any digital twin that wants to join that initiative actually needs to meet these different 9 Gemini principles, and in our case we'll be digitalizing the West Side Cambridge campus. Now, we think digital twins are represent the convergence of the emergence technologies in AEC and facility management industry. We had BIM representing the new way of, let's say, modeling our information about buildings, storing it and sharing it, with IFC being the main means for exchanging information between systems. We've got different ontologies to help us standardize the way we are modeling information about physical, logical, and digital or virtual assets. Now, we have many different definitions of what a digital twin is, but unluckily many of them they just are limited to just BIM or 3D modeling, and we think that we need to steer away from that definition of a digital twin. So we instead embrace this 3-tier definition, in which we think like a digital model is just the static representation of the physical counterpart. The digital shadow, it's the dynamic representation of that physical object. So when monitoring comes into place, and then that means that there is a data flow from the physical world to the digital environment. And then last but not least, the digital twin is, we cannot talk about digital twin unless we talk about actuation, which means that there is some interaction between the digital and the physical world. And so let's say if you change one of them, the other will be affected in some sense. Now, in the operations and maintenance phase, it's normally characterized by independent system functions that they are focused on the effective and efficient operation of their equipment. And so these different systems, they don't communicate so often, and even they are managed by different companies. But we think that this segregated world we can enable that communication by the use of digital twins. But the development and implementation of these digital twins is not a path of roses. Normally, we will start in data acquisition, having problems on just getting on-demand access to this segregated data in these different systems. And this natural segregation of data means that the information is modeled to meet the requirements of these different systems. Having a centralized model that combines all of them is not an appropriate approach neither, because it can become unmanageable really quickly when new uses of data come along. In terms of data integration and data quality, with this segregated data, obviously having on-demand mapping of this variety of sources can be a nightmare, and even more when we have multiple versions of the data that we are managing in these systems. So, for instance, if we are talking about a building, there's not the same having the definition of the building as designed, as built, or as it currently is, because actually buildings evolve with time. And this can be even worse when data on those models are not complete or not accurate at all. And then in terms of management, the storage and provision of high velocity data, so when IoT comes into place, can be really resource consuming. And so the processing of all the data sources that we may have available. Now, so semantic web approaches, they've driven the integration of these different system data, but again, having a common model or a common ontology that combines all these worlds, it's again not very manageable because of the new uses of data. And we've seen a lot of initiatives trying to put all of them together, coming with Frankenstein ontologies and models. So instead we are adopting the federation approach, which is actually one of the key principles in our consortium. And it talks about that if we have federated data models, we can promote domain specific independence of data sources, while actually finding the appropriate links between these all ontologies to standardize the integration of data. Now, we can keep this independence of the data sources and just integrate all that data into operation and maintenance applications. And we feel like data lakes are a natural fit for this kind of model, because they actually keep that independence of the original data sources. Now, we think that to this model to be successful, we need to start from the application side as well. So we gather all the different information requirements for the applications and then go and find the data for them. And then use the different ontologies to actually enable that integration. Now, we're going to present the case study based on our building, the Alan Reece building in the West Side Cambridge campus. And the case study talks about a fault detection and diagnosis tool that our facility manager was interested in. We're just using Rick here to explain a little bit how the HVAC system works, which is the goal of this FDD application. Really simplified, we have like an HVAC zone that is composed of different rooms, and there's some equipment that feeds the heating and cooling for those rooms. And there's going to be different sensors at different levels to monitor this equipment or these elements. Now, again, to define these applications, it doesn't matter if it's fault detection or diagnosis or any other type of operation application to promote facility management, we need, again, to start from the information requirements and then go straight to the data sources to find out where the appropriate data to meet those requirements is. And then we can integrate that data through specific pipelines that go towards the applications and enable the access of that data through APIs. Now, the integration can happen on different levels, and we'll see that in more into detail. So for our particular case, we were really interested on real-time data access for this application. So the facility manager could have a quick answer to any fault happening in the building, more specifically in the HVAC system in this case. And for that, our answer was indexing and memory storage for all the data coming throughout the data lake in the pipelines. And so we defined two different data pipelines, one to gather all the data from the BMS, so the different system functions and relationships and the sensors that are attached to the equipment, in this case the HVAC system. And again, that was transformed through the pipeline into a format that could be indexed and stored in memory for quick access. And then for the BIM data, we were using IFC to drive that integration and to transform that into the same kind of a format. But in this case, it's a lot more static because the BIM information doesn't change that often. And after that, we could integrate into another pipeline these two pieces of information and make it available to the FDD application. Now, to complement all the sensors attached to this system, we have an IoT deployment to monitor the different spaces. And with that IoT deployment, we had this real-time data stream into the FDD application. So every single data reading from the sensors could be tagged with the appropriate geometric and system information before reaching the application. Now, this is a really quick result of the data integration, but I'll just leave it for whoever is interested to go into the paper to see the details. Now, I'll be focusing more on actually what is the logic of that application, how the information actually flows. So we start with a number of sensors that we'll be monitoring, right? And then when one of the sensors just makes a warning and maybe a potential fault is detected, then we go and check all the related elements to that sensor. In this case, it was a HVAC zone again, and the related rooms to that. And we'll need to check as well what is the equipment that is feeding that room, right? And at the same time checking all the different monitoring points that we've got for that equipment. If we've find the problem, that's fine. We've diagnosed the reason of the fault. Otherwise, we keep on going with the surroundings of that equipment and those spaces. Now, we've kind of demonstrated how to integrate systems, functions, geometries, and real-time data from the IoT. And the conclusions that were drawn are that the data integration and digital twins are technologies that enable the smart building operations, but it's only possible when we face when we tackle the technical challenges of this data engineering with planned application development, which just means we need to start from the application side requirements. And then we acknowledge that on-demand access to the original sources remains a big challenge because of the change of responsibility of data, especially when there's different companies managing those systems. But our federated approach for data models can sort of ease this burden by maintaining the independence of the original sources. Thank you.
Okay, thank you very much for the presentation, really nice. And the floor is open for a few questions. We have 5 minutes. Okay, we have one here. I also have questions.